Take any positive integer. If it is even, divide by 2. If it is odd, multiply by 3 and add 1. Repeat this process. The Collatz conjecture asserts that regardless of the starting number, this sequence will always eventually reach the number 1. This deceptively simple arithmetic operation defines the 3n+1 problem, a notorious challenge in number theory since its proposal by Lothar Collatz in 1937. The rule set is elementary school level, yet proving its universal convergence remains one of mathematics' greatest open problems, resisting all attempts by leading mathematicians for over 8 decades. The conjecture implies that no starting number generates an infinite sequence, and no starting number enters a non-trivial cycle. The Collatz function, C of n, is formally defined piecewise. C of n equals n divided by 2 if n is congruent to 0 modulo 2. C of n equals 3n+1 if n is congruent to 1 modulo 2. The conjecture states that for every n greater than 0, there exists an iteration k such that c superscript k of n equals 1. Consider the starting value 6. 6 is even, so the next term is 3. 3 is odd, resulting in 10. 10 is even, yielding 5. 5 is odd, producing 16. 16, 8, 4, 2, and finally 1. This sequence, 6, 3, 10, 5, 16, 8, 4, 2, 1, demonstrates convergence in 8 steps. The maximum value reached in this trajectory is 16.
The only known cycle is the trivial cycle, 4, 2, 1, which repeats indefinitely under the Collatz map. A non-trivial cycle would be a sequence of distinct integers greater than 1 that returns to its starting point. The existence of such a cycle would immediately disprove the Collatz conjecture. Alternatively, a counterexample could be a starting number whose sequence diverges to infinity. Extensive computational verification has established that no non-trivial cycle exists and no sequence diverges for starting values up to 2 to the power of 68, a bound established by Tomás Oliveira e Silva. The search for a counterexample is equivalent to searching for a number that does not converge to 1. The current verification limit confirms that all starting integers up to approximately 5.76 times 10 to the power of 20 converge to 1. This massive computational effort, primarily utilizing distributed computing projects, provides strong empirical evidence but does not constitute a mathematical proof. The verification process involves checking the trajectory of each number until it drops below the starting value, ensuring it eventually enters the known path to 1. The computational bounds are constantly being pushed, but the sheer size of the search space highlights the difficulty of finding a counterexample, if one exists, especially since the maximum height of trajectories can grow rapidly. Heuristic arguments suggest that the sequence should decrease on average. When a number is even, the operation is multiplication by 1/2. When it is odd, the operation is multiplication by 3n+1, followed by division by 2 in the next step, resulting in a net multiplication factor of 3/4 over 2 steps. Since roughly half the numbers are even and half are odd, the expected multiplicative factor over 2 steps is approximately the square root of 1/2 times 3/4, which is less than 1. This probabilistic drift towards smaller numbers supports the conjecture. However, this heuristic ignores the specific ordering and dependencies between consecutive terms, meaning it is not a rigorous proof.
The total stopping time, denoted by sigma infinity of n, is the number of steps required for the sequence starting at n to reach 1. The maximum height of a trajectory is the largest value attained before reaching 1. For example, the number 27 requires 111 steps and reaches a maximum height of 9,232. Analyzing these trajectories reveals highly erratic behavior, often described as pseudo-random, despite the deterministic nature of the rule. The complexity arises from the interplay between the multiplicative 3n+1 step and the division by 2 steps, which prevents simple linear analysis. The Collatz problem is a specific instance of a general class of iterative functions known as 3x plus beta problems or generalized Collatz mappings. For example, the 5n+1 problem exhibits divergent behavior and multiple cycles, demonstrating that slight modifications to the rule drastically change the dynamics. The study of these generalizations, such as the k-Collatz sequences, helps isolate the specific properties of the 3n+1 rule that might force universal convergence. Understanding why the 3n+1 rule appears unique in its convergence property is a key research direction in number theory. The Collatz map can be viewed as a discrete dynamical system on the positive integers. The sequence generated is an orbit, and the conjecture asserts that all orbits eventually lead to the fixed point at 1. The erratic nature of the trajectories suggests connections to ergodic theory and normal numbers. John Horton Conway demonstrated that generalizations of the Collatz function can simulate Turing machines, implying that predicting the behavior of these sequences is algorithmically undecidable. This connection suggests the Collatz problem itself might be inherently complex, potentially requiring entirely new mathematical tools for resolution beyond traditional number theory.
The Collatz conjecture remains open, classified as one of the most difficult unsolved problems in elementary mathematics. Paul Erdos famously stated that mathematics is not yet ready for such problems. The difficulty lies in the lack of structure preservation. The 3n+1 operation destroys modular arithmetic properties, making standard number theoretic tools ineffective. The American Mathematical Society offers a $1,000 prize for a proof or disproof, reflecting its status as a foundational challenge. The resolution of the Collatz conjecture would likely introduce revolutionary techniques applicable across number theory and discrete dynamical systems.